This is notes number 5 in Mr. Sweeney's AP Physics C class for the energy unit, talking about universal gravitation and Kepler's law. Universal gravitation describes the gravitational force of attraction between any two masses and is determined by the formula force of gravity equals the gravitational constant times the mass of both objects divided by the distance between their centers squared. And we talked about this initially within our forces unit, and we're going to talk about the energy associated with gravitational force outside of our planet. So we've been looking at energy as mass times gravity times the change in height, but that only works on, say, the surface of a planet where you're in a constant gravitational field. If you go and you look at astronomically large bodies or heavenly bodies, the gravitational force and the potential energy associated with those forces is different than MGH. So let's look at the potential energy. Gravitational potential energy for bodies with masses of similar magnitude, so planet to planet, a sun to a planet. We're not talking about objects on the surface of a planet, but one astronomically large body to another, or one very small body to another. That can be expressed with the following formula. The potential energy gravitational is equal to the gravitational constant multiplied by both masses divided by the distance between centers, and that is the gravitational potential energy. We'll talk more about where this formula came from in class. When we're looking at gravitational potential energy, the change in the gravitational potential energy does not depend on the path taken. So it doesn't matter how twisting and winding the path may have been. All that matters is where you start and where you end for the change in this gravitational potential energy. The work done to move between these 2 points in the gravitational field is equal to the change in the gravitational potential energy. This is because the gravitational force acting on it is conservative, and we know that conservative forces, the path taken between the start and finish positions, does not depend on the work done, or the work done does not depend on the path taken, excuse me. And if we have multiple masses acting on one another, the potential energy follows the law of superposition. Superposition, if you remember, states that if you have multiple influences coming from multiple objects, multiple sources, that to find the total influence, you just add each influence together as vectors. So this is vector addition. If there's more than one object that's applying a gravitational potential energy to another object, you add up all their energies like they were vectors. One of the interesting consequences of gravitational potential energy is this idea of escape velocity. So escape velocity, that is how much speed, how much velocity you must give an object initially in order for it to leave be able to escape the gravitational pull of an object. So how fast must a rocket be traveling in order to make it off the Earth? And we figure out what the escape velocity is by setting the gravitational potential energy of the object at its position equal to the kinetic energy you would need. So if you have enough kinetic energy there to overcome the gravitational potential energy, you'll be able to escape the gravitational field. Setting these two equal to each other, you can solve for the velocity component that is part of the kinetic energy equation, and you get the velocity, the escape velocity, equal to the square root of 2 times the gravitational constant multiplied by the mass of the object that you're trying to escape from, and then dividing that by r. The mass in this equation is, say you're trying to escape Earth, you would use the mass of the Earth. This brings us along to talk about Kepler's 3 laws and satellites. If we're looking at gravitational potential energy, we want to be able to study the motion of astronomically large bodies like planets, moons, the sun. You can even take it to be galaxies. You can look at satellites, objects orbiting around different planets or moons. And Kepler's three laws will help us to understand the way that these heavenly bodies move. So the first of his three laws is the law of orbits. This states that all planets move in elliptical orbits with the sun at one of its focus. If you recall back from your earth science class, when you have an elliptical orbit, the object moves around two focuses, one being the object it's orbiting, the other one being an imaginary point. And we can see this down here. Here we have the sun on the left here. This is our elliptical orbit. And the sun is one of our two focuses. The eccentricity of this ellipse, how elliptical it is, depends on the distance between the two foci. The closer they are to the center, the more it is a circle. The more that the two focuses depart from the center, meaning it has more eccentricity, the flatter the oval will be. That will be the ellipse. Kepler's second law is the law of areas. This says that a line that connects a planet to the sun will sweep out equal areas in the plane of the planet's orbit in equal time intervals. What this essentially accomplishes is they're sweeping out equal orbits, that when the planet becomes closer to the sun, it will increase its velocity. It needs to increase its velocity so it can sweep out greater areas. So as a planet, this could also apply to like a satellite around Earth or a moon around a planet. But as the orbiting object approaches, it gets closer in its orbit to the object it's orbiting around, it will pick up speed, and then as it moves away and gets further away from the object it's orbiting around, it will slow down. So this law captures this idea of a varying velocity of the object as it gets closer and farther away from the object it's orbiting around. And his third law states that the square of the period of any planet is proportional to the cube of the semi-major axis. The semi-major axis, I'm hovering over it with my mouse here, is this distance from the center of the orbit to the outer edge. So it's the long side of the ellipse, but only half of that distance. One thing to note is that because the semi-major axis never changes its size regardless of where it is in the ellipse, that means that the period of the planet is always going to be constant. And we see that with our own planet. Earth's period as it goes around the sun is 365 1/4 days. That doesn't change year to year to year. So even though we move quicker at some points and slower at some points as we move around the sun, our ellipse is more or less circular. This doesn't change, so the period is always the same regardless of the fact that the velocity of the object that's orbiting is varying. And there's an equation that's associated with the law of periods. And that equation is the period, that's capital T squared, divided by the radius. That would be the radius for a circular object. It could also be the semi-major axis length for an elliptical orbit. So the period squared divided by this radius or semi-major axis length cubed is equal to 4 pi squared divided by gm. Let's talk about the energy that's captured within the satellite. When you're looking at the energy of the satellite or planet, it can be determined from its orbit, but it remains constant throughout its path. As it gets closer to the object it's orbiting around, it picks up speed. But as it picks up speed, the potential energy decreases because the distance between the two objects is decreasing. So as the potential energy gravitational decreases, the speed increases. The kinetic energy increases. As the potential energy gravitational decreases, it moves away from the object. The speed decreases. So we have a varying change here. The kinetic energy plus the potential energy, gravitational, will always equal the same amount. And we can figure out what this energy is with the following equation. The energy is equal to the negative gravitational constant multiplied by the two masses, and then divided by 2 times the distance between centers. And here we use the r, the distance between centers. For a circular orbit, that is just the radius. If you're looking for an elliptical orbit, that r would be the semi-major axis length. So it would be the length at its furthest point from the object. And we could take a look here at the kinetic energy of satellites. For elliptical orbits, the velocity of the satellite or the planet, it's variable. It varies along its path. So the kinetic energy depends on the distance away from its orbiting. This is because that kinetic energy must compensate for the change in potential energy, always equaling the same amount of energy that's there. To find this kinetic energy, we use the equation kinetic energy is equal to the gravitational constant times the two masses divided by 2r. And again, this r for a circular orbit would be the radius, and for a elliptical orbit, this r would be the length of the semi-major axis. And this will conclude our discussion